Hello, everyone. My name is Joann Roberts. I'm a student at Chicago State University, an undergrad majoring in engineering physics. And the goal of this summer's research was to learn and execute exoplanet hunting using two methods, radio velocity and astrometry. This included rediscovering, for the sake of getting my feet wet, a Jupiter-like exoplanet around the star HIP 11915 by plotting given RV data from a telescope in Chile to create an RV model, then calculating the RV and astrometric signatures. So just a little background, an exoplanet is a planet that orbits a star outside of our solar system. This image right here is the first one taken of an exoplanet back in 2004, orbiting a brown dwarf. So if you look at the XYZ planes, RV is in the Z direction, astrometry is in the XY directions. We eventually wanted to use both since one is one dimension only and the other is two dimensions, combining for 3D observation. Radio velocity is important because it was one of the first successful ways to find exoplanets and is still very productive today. It is also used to confirm planets found with other methods such as astrometry. So this summer, we initially used the RV method to get to astrometry. Now, what you see here is a NASA animation that visualizes radio velocity. Now, radio velocity is defined as the velocity of a star or other body along the line of sight of an observer. The RV method for detecting exoplanets relies on the fact that a star does not remain completely stationary when it is orbited by a planet. The star moves ever so slightly in a small circle or ellipse, responding to the gravitational tug of its smaller companion, as you can see in this animation. Since RV looks at one dimension only, you only see the star moving back and forth. And even though it is a projection of that circle, so we watch for the wobble since it is a star's wobble that can tell you if it has any exoplanets. Over 800 exoplanets have been discovered using radio velocity. Now, what does RV look like in data plots? This lovely drawing I put together shows radio velocity as a function of time and is a plot of where the star is at different times in its orbit. Time is on the x-axis, identified as Julian days, where 1 in JD is 24 hours, and it shows a full cycle of elliptical orbit over a period of time. The y-axis is the RV, or the amplitude of the wavelength, which is the absolute amount of velocity, or the total speed it's moving and the amount it changes in orbit. This can be translated into planet mass, which sets how hard the planet is tugging, and the strength or gravitational force of the tug determines how fast the star moves in response. Now, we as an observer can only see the star and the planet is hidden from us. We know that when the star is moving toward us, it is a negative radio velocity, and when it moves away from us, it is positive radio velocity. So we can only measure the component that is headed toward us. We measure at maximum negative velocity and maximum positive velocity, which is shown here in the graph on the red vertical lines. Orbiting through zero velocity represents the highs and lows of the wavelength, moving from negative RV to positive RV. So at the black and yellow parts of the drawing, we only see the partial RV, and at the blue point, we see none, which is zero velocity. So overall, this is the elliptical motion in the line of sight in and out of the sky. So we used a paper that my mentor, Megan Bedell, helped to write, titled The Solar Twin Planet Search, to help with the equations and parameters, as well as a two-body link that gives code to compute and plot RV and astrometric curves using given orbital elements and barycenter motion. I used the Python Jupyter notebooks to solve some of the math for Keplerian orbits, specifically writing code that would take a set of orbital parameters, like the period of the orbit and the mass of the planet, as well as the different angles in the orbit. Using several years of data from the HARPS telescope in Chile, I was able to plot HIP's motion and recreate the figure drawn in the previous slide, where we translate between the star's motion and what we observe, therefore calculating the RV of the Jupiter-like planet. The curve is the model of the Keplerian motion that we optimized to fit the data. I was able to see the wiggle and translate them to see what the star is doing through its orbit, because the shape of the RV curve encodes info about the star planet system and the planet's orbit. So as you can see, there is a slight offset in the RV curve and that it's not exactly centered around zero. It was the way we normalized the data, but in reality, the relative velocity is the data that matters, and it's hard to measure the absolute value of the radial velocity. So this is just the way we normalized it. So as you can see, the curve matches the data pretty well, and we were able to conclude from the data that we rediscovered a Jupiter-like exoplanet. Now to touch on astrometry. These next couple of animations are from the European Space Agency. Astrometry is defined as the measurement of the positions, motions, and magnitudes of stars. It is related to RV in that this technique can also be used to identify planets around a star by measuring tiny changes in the star's position as it wobbles around the center of mass of the planetary system. The astrometric method for detecting exoplanets involves detecting the star's position wiggling around in space. The line is tracking the star across several decades of time, and the wiggle represents another orbit of the planet happening or a new orbital cycle. Now, we've only been able to find one exoplanet so far using this method. Why is that? Well, looking for minuscule movement proves to be quite difficult, making smaller planets harder to detect. It requires perfectly accurate optics, and our view from Earth is subject to bending and distortion of light due to our atmosphere. However, the Gaia missions look to change this and will revolutionize astrometry as it is the future of exoplanet hunting. Lastly, this is a plot of the astrometric symbol, or a signal, I should say. Whether it's a wiggle or a circle depends on how the star is moving and has to do with where the observer is looking from. So this is showing the proper motion where the observer is moving right alongside the star and they are staying relative to each other, which explains the lack of wiggle. So we made it so that the star isn't moving across the sky and the circle is actually due to the planet. Now for the fun stuff. Aliens. If an alien were observing the solar system to discover planets, what would they be able to find? Which planets are easiest to discover? What kind of observations are needed? Most importantly, could they find us? The reason we've been interested in Jupiter-like planets is because that's probably the first thing aliens would see in our solar system. While we didn't get a chance to prove aliens would discover Jupiter first, we do hypothesize that based on what we know about the RV and astrometric signals, as well as their equations, that we can derive and show that the aliens would be able to discover Jupiter first. Well, how is this? Well, wobble depends on the mass of the planet and the distance between the planet and the star. So larger planets tend to have more wobble, and Jupiter is the most massive planet in our solar system. So per the twin solar planet reading and radial velocity, if a planet is close to a star, then it has more g-force, so you get a bigger signal, and signal size changes with the mass of the planet in its orbital period. It also depends on where they are, as certain inclination and distance to us would make RV signals detectable. So for the sake of fun, we'd like to speculate that they are close enough to us in this scenario. Either that or they've combined RV and astrometry, if that's the methods that they're using, into 3D, which cancels out inclination. A lot of exoplanets have been hot, closer to the star configurations with shorter years, and we don't have those kind of things in our solar system. So given all of this, Jupiter would be easier to find than, say, Earth. But maybe once they find Jupiter, they'd be able to get to us from there. In conclusion, I've explained how RV plots work in view of time versus RV and how you can determine what kind of planet it must be. We also touched on the astrometric method and it being the future of exoplanet hunting. So why do we search for exoplanets? Well, because we're natural explorers and we want to know whether or not life exists outside of our solar system, ultimately answering these questions. Are we alone in the universe? Are there other habitable worlds? How does the universe work and where do we fit into that? And how are planets made? I finally learned some Python and have been reminded why discovery is the backbone of scientific exploration, as well as why this particular field of science influences nearly every aspect of my approach to life, from my creativity as an artist to my passions for teaching and wanting to share this stuff and also teach it through the arts, to traveling and exploring our planet. So I'm interested in doing more exoplanet hunting as well as understanding neutron stars and black holes in graduate school. And I feel this program has gotten me a step closer to my future in astrophysics and science education. With that said, I want to say thank you to NSBP, Simons Observatory, Casey Wagner, my wonderful mentor, Megan Bedell, and everyone else involved in making this such a great fellowship program. This concludes my presentation.